Okay, so in this video we're looking at something called the standard normal distribution. Now, you've seen normal distributions before. Now, for instance, people's heights are normally distributed. That means that, say, if the average height in a town or a city or a country is 175 centimeters and the standard deviation is, say, 5 centimeters, that means that 99.7% of all people will be within 3 standard deviations of 175. So if the standard deviation is 5 centimeters, that means that 99.7% of people will all be within 190 to 160 centimeters tall within that particular place, whatever it might be. Now that's the normal distribution. It's the mean and the standard deviation can be pretty much anything you want it to be. Now, something that can be done, and new year 12s will, it'll happen behind the scenes when you do your QCS test and when we compare your class ranks. Normal distributions can all be standardized to something called the standard normal distribution. Now, the standard normal distribution, really, it's fairly straightforward. Same shape, it's still a normal distribution. This time it has a mean equal to 0, and it has a standard deviation equal to 1. That means that all, 99.7% of all values in a standard normal distribution fall between -3 and 3. Sorry for the shadows. Now in today's lesson we're going to be asking questions like what is the probability of values being less than, say, 2.2? So what's the probability that things will fall under here? Or what's the probability that something is more than -1.5? And we'll go over here. So that's what we're going to be doing today. We're going to be looking at probabilities less than, greater than, and in between two different values. Let's just throw some light on this thing. Okay, so we're going to do a few questions here so you can see what this looks like. This is purely mathematical stuff. Later on we'll go into some of the applications, I guess. Okay, so you might get a question that looks like this. Find the probability that Z is less than, well, let's do 2.2 like we had it over here. Okay, we're going to use our calculator all through these questions. So there's a lot of things that you're going to have to do here with your calculator. So make sure you've got your graphics calculator out and ready to go. Now here's my calculator. Now before we get started, there's a few quirks of the maths here that means that if we're going to be really pedantic about this, we need to be really, really careful. Let me show you what I mean. Draw you a little picture. Here's our x-axis, here's our y-axis, I guess, and our standard normal distribution looks something like this. Now, the area under the curve is equal to 1. So, in other words, the probability that something happens, that anything happens, is equal to 1. So if we were in terms of our heights, what they're saying is the probability that someone has a height is equal to 1. That's pretty straightforward. Now the problem with our standard normal distribution is that these tails go on forever. There's an asymptote here at y equals 0, which means that they go on forever and ever and ever and ever and ever and ever and ever, never ever touching the x-axis. And these go on forever and ever and ever and ever and ever, never touching the x-axis. Now, I'll leave it to you to ponder the weirdness of why this probability can be equal to exactly 1 when it actually never ever touches the x-axis. You're just going to have to believe it to be true at this stage, or we can get into an argument about limits if you want to in class. Okay, so what that means for us is that if we want to do a probability that Z is less than 2.2, we kind of can't really come at it directly. What I mean by that is that we can't say, okay, here's 2.2, let's find all of this. and I'll show you why on our calculator. So in order for us to use our calculator, I'm going to go into something called stat mode. I'm going to go into the distribution, and we're interested in normal distributions. Now we're always going to use NCD here, or at least for the foreseeable future. Now it's come up in a weird view, it's come up in the list view. You need to be in the variable view. Okay, now what this is going to do, I'll actually show you what it does. I'm going to give a lower score of 0, an upper score of 2.2. Now normal distributions have a standard deviation of 1 and a mean of 0. Okay, so just looking over that, we're using a cumulative distribution under the normal curve. We're having a lower value of 0, an upper value of 2.2, a standard deviation of 1 and a mean of 0. Whenever you're dealing with standard normals, you'll always have 1 and 0 here. I'll go down a bit further. Okay, a bit further. It comes to execute and this little draw button here. I'm going to draw it. Okay, you can see it's drawn me a really nice normal distribution. And it's given me a lower bound of 0, an upper bound of 2.2 right here, and it's found the area under that curve. Now the area under that curve is 0.486. Now I've chosen 2.2 here because we wanted to know the probability that Z is less than 2.2. Now when I said we couldn't come at it directly, what I meant was, if we wanted to come at this directly, what would we put in as our lower value? Would we put in -3? Because that would cover almost all the values, but not quite all of them. Would we put in -4? Again, almost all of them, but not quite. Would we put in -100? What we know is that this limit goes on forever. So no lower bound on my calculator is going to be sufficient to do this in a mathematically correct way. What I can say, however, is that the area under this bit here is equal to 0.5. So it's no accident that I chose a lower bound of 0 and an upper bound of 2.2. When I draw it, and I suggest you always draw them, when I draw it, I know that the probability of this happening is 0.486. I know that the probability of all of this stuff happening, all the way out to like Z is a -1,000,000 or something, is 0.5. So the total probability of Z being less than 2.2, in other words, and it's always a good idea to draw these, in other words, all this is equal to 0.5 plus 0.486. That's going to be 0.986. So there's a, not percent, there's a 0.986 chance. If we wanted to write it as a percentage, we could. It would be 98.6%. So that's the probability that Z is less than 2.2. I know it looks like I'm being really pedantic here, but it's very important that we understand that we can't come directly at a question like that. We're going to do a bunch of these ones to see how they all work. Okay, so here's my second question here. The probability that Z is greater than -0.5. Now, first of all, draw it. Here's our normal distribution. Remember, it has a mean of 0. We want to know the probability that Z is greater than -0.5. So I'll find the -0.5. Obviously, it's to the left of here. And we want to know the probability that Z is greater. We want to know all of this stuff. Everything greater than -0.5. That's an arrow. Okay, now again, we can't come at it directly, so we need to do it in 2 stages. We know that that area is 0.5, so we just need to find this bit. Now, if I wanted to be really formal about this, I would say that the probability that Z is greater than -0.5 is equal to 0.5 plus the probability that negative 0.5 is less than z, which is less than 0. Okay, so a really nice formal way of setting this out. I'm finding 0.5 here, and I'm finding the probability that z is between negative 0.5 and 0. On our calculator, very, very simple. A lower bound of negative 0.5, an upper bound of 0. Now, if you just click execute, it'll just give you an answer, but I highly recommend actually drawing it. So you can see that what you drew on the page is the same as what comes up here. So 0.5 plus 0.19, you probably should go to 4 decimal places. I couldn't be bothered right now, so I'm not going to. 0.69. Okay, so two very, very similar questions. They were pretty much mirror images of each other. But there are a bunch of other ones that are very similar. Okay, so here's our third example. Sorry, I'm going all over the page here. Maybe we'll go to another page in a minute. Now, probability that z is greater than 0.8. Now, as is the case here, every time you do one of these, you really want to draw it. So, simple, normal distribution. 0 is our mean. And we want to know the probability that z is greater than 0.8. So there's 0.8. We want to know the probability in here. We want to know all that section. Now again, we can't go to it directly, but we do know that this is 0.5. We can find this, and then we know that z is greater than 0.8 is going to be equal to whatever all of that is minus 1. So in a really formal way, we could say that the probability that z is greater than 0.8 is equal to 1 minus 0.5, that's the 0.5, minus the probability that that 0 is less than z, which is less than 0.8. Really convoluted way of doing it, but if you draw your pictures and then try to match it up with the calculator, you shouldn't have too much trouble. 1 minus 0.5 minus, and we want to know, oops, go back to normal distribution. We want to give it a lower bound. We want to find this piece in here, because we know what this piece is. We know the whole thing is 1. If we know this piece, we can find this piece. 0, upper bound, 0.8. Don't forget to draw it. That's what we want, and it's 0.288. Now, don't like jumping from thing to thing in my calculator, so here's number 2. 1 minus 0.5 minus 0.288. So the probability that z is greater than 0.8 will be 0.212. Okay, so hopefully you're getting a feel for how this all comes together. You pretty much always have to find like an internal part, whether that internal part is that piece here, or this piece here, or this piece here, and then work around that in some way. We might take a look at one or two more. Actually, change my mind, guys. I think we're good there. Really, you're going to have to practice these, and make sure you're talking to me about whether your working is appropriate or not. Also, make sure every single time you do it, you draw a picture. Now, they can be very, very rudimentary pictures. They don't need to be anything flash, but you need to show that you understand what you're doing and what your calculator should be doing as well. All right, guys, that's it. I think we're finished here.